In this segment, we're going to load the scan from our previous experiment. So we click on Load and select the scan of the 31.4 centimeter patchcord cable. It's an SMF28 cable, and we use an 81642A tunable laser. Press OK. The raw scan pattern shows up, and this raw scan was generated by the Fabry-Perot interference pattern formed by the FCPC connections in our fiber, so the device under test. We press OK because we're going to use the full scan bandwidth. Now what are we doing here? So this power spectrum is the power spectrum of the scan. So if we increase the number of points in our spectrum, we're looking for the peak. Now what's the peak? The peak is the frequency of that raw scan Fabry-Perot interference pattern. And why we're looking for it is because that's going to give us the group delay in that device, or the group delay difference between the reflections from the front and back facets of the device. Now we need that group delay because we're going to multiply this raw scan pattern by a simulated interference pattern, and that simulated interference pattern is going to be simulated free space Fabry-Perot interference pattern with the same group delay as the device under test that produced the scan. So we're going to multiply two interference patterns together, and that's going to generate a second order interference pattern, and it's the envelope that we're most interested in this pattern. So when we increase or decrease our resolution, that basically is a coarse balancing. We're finding the balance point. We're looking for the group delay of the device under test, and by moving around this coarse balance, we get further away from our balance point, or closer to our balance point. So what we're going to do is we're going to leave it here, and we're going to increase our sensitivity. Okay, and what's this? This is basically the amount by which we change our virtual path length. The path length, it's basically the reference path. It's a virtual reference path. And we're changing that path length in order to get closer to our balance point. Now again, this is optional, but doing it manually might make the experiment run a little bit faster, particularly because we're using an 81642A tunable laser. It's an older laser, it doesn't have the same as good of a linearity. In any event, we're looking for the central wavelength. This is the center wavelength, the large hump in the center, and then what happens is that the period between the peaks gets shorter and shorter. And what's the significance of this central location? It's the location where the group delay is balanced. So the group delay in the test device, or the group delay difference between the reflections that form the cavity around our test device, are equal to the group delay difference in the virtual cavity. Okay, so the reflections. And once we've done that, we can press OK. So in this step, we are fitting to our envelope. So we're creating a first order interference pattern by fitting to the envelope. And this first order interference pattern is equivalent to what would be produced in a traditional dual arm interferometer. So a two-wave mix, interferometer. So in this step, we have our fit pattern. Now, just a few points. How is the group delay calculated? Well, the center wavelength, the location where the group delay is balanced in the virtual, where the virtual cavity is equal to that of the real cavity, it's calculated by looking at two peaks on both sides of this central wavelength. So we need to have at least 2 peaks to calculate group delay. The second order dispersion, so that would be group velocity dispersion, or if you prefer, the dispersion length, the dispersion parameter. That's calculated by looking at the separation between the peaks, the 2 peaks. So this distance on the left and right side of the center. So if we're producing group delay and second order dispersion plots, we can move this center wavelength to the left or to the right only as far as we have the 2 peaks on both sides of the interference pattern. Okay, so the bandwidth of our scan is going to be greater than the bandwidth of the results. And this is characteristic of all balanced, dual arm balanced interferometric techniques. So once we have, one of the key points here is to remember is we don't want to increase the fitting parameter too high where we have more than one peak, more than one X for every peak. We want to keep the X's always above this green line. Okay, so once we have that, we try to get as high a contrast as possible, because that gives us good results. And then we press OK. So the system is going to automatically balance now, which is very quick because we were close to balance. Then it's going to find the leftmost point, how far we can shift the interference pattern to the left, and how far we can move it to the right, and it divides that by 50 points. And now it's calculating. It's changing the virtual path length of the virtual interferometer, or the virtual cavity, multiplying the resulting interference pattern by the raw scan, and then producing the fit that you see here, and then generating the results. So this is our dispersion, this is our group delay. So this is the plot of the group delay. This is our group velocity dispersion, and this is our dispersion length. Note that GVD and dispersion length are both second order, different ways of looking at second order dispersion. So again, we can always export the results. You can export them to your desktop and just say results. Sorry, I typed that wrong. But we can export our results, and you can open them in an Excel spreadsheet, or in MATLAB, or as a text file. If you add the .text, you can add .text to the file, so you can say results .text, and it'll save it as a text file for you. So again, thank you very much for viewing our videos, and if you have any further questions, or any questions at all, please don't hesitate to contact us. You can always email us at sales@inametrics.com, or contact us. You can see our contacts page on our website, and the website is www.inametrics.com. Thank you.